What if the universe itself is the ultimate blueprint for the next technological revolution? Picture this: deep in the vast, silent expanse of space, hidden within the swirling mysteries of black holes, the strange dance of dark matter, and the eerie whispers of pulsars, lies the potential to reshape our entire future. We're not just talking about incremental advances, but leaps so profound they could redefine what it means to be human. Think of propulsion systems powered by the same forces that propel galaxies apart, or communication networks that harness the quantum chatter of distant stars. These aren't scenes from science fiction, they're real ideas being explored by scientists right now. And they all start with one simple truth: the cosmos is far more than a backdrop to our existence. It might just be the greatest untapped resource we've ever encountered. For centuries, humanity has looked to the stars with wonder, but today, we're beginning to see them as something else: a cosmic instruction manual. Every unexplained phenomenon, every unsolved riddle out there could hold the key to technologies we've barely dared to imagine. Take dark energy, for example. This mysterious force, driving the universe to expand at an accelerating rate, might one day fuel spacecraft capable of reaching other solar systems in a fraction of the time it takes now. Or consider pulsars, those incredibly dense, spinning neutron stars that beam radiation across space like cosmic lighthouses. Their precise rhythms could inspire ultra-secure quantum communication networks, impervious to hacking. Even black holes, those gravitational monsters that warp space and time, might teach us how to manipulate energy in ways that seem like magic today. This isn't just speculation, it's the frontier of science. Laboratories around the world are already experimenting with concepts that sound like they belong in a futuristic novel, all because we've started asking one bold question: what if the universe's greatest mysteries aren't just puzzles to solve, but tools to wield? In this video, we'll journey through the most exciting theories and experiments bridging the gap between cosmic enigmas and real-world innovation. You'll meet the brilliant minds daring to dream big, and you'll see how their work could transform everything from energy to computing, from transportation to medicine. So buckle up, because by the time we're done, you might never look at the night sky the same way again. The future isn't just written in the stars, it's waiting for us to reach out and take it. The universe doesn't just hide its secrets, it taunts us with them. Take dark matter, that invisible substance making up nearly 27% of the cosmos. We can't see it, we can't touch it, yet its gravitational pull holds galaxies together like cosmic glue. Now imagine if we could harness that power here on Earth. Scientists are already probing this possibility, studying how dark matter's properties might unlock anti-gravity technologies or energy sources beyond our wildest dreams. Picture cities floating effortlessly above ground or spacecraft gliding through the solar system without fuel. This isn't fantasy, but physics waiting to be decoded. Then there are black holes, nature's ultimate energy factories. Their intense gravitational fields spin matter at nearly the speed of light, converting mass into pure energy with staggering efficiency. What if we could replicate that process on a smaller scale? Researchers are exploring analog black holes in labs, using sound waves and plasma to simulate their energy conversion mechanisms. The implications are staggering: clean, nearly limitless power drawn from the same principles that govern the most destructive forces in the universe. Even cosmic rays, those high-energy particles bombarding Earth from deep space, hold technological promise. their ability to penetrate almost any material could inspire new imaging technologies for medicine or security. Some scientists believe these particles might even help us develop quantum processors that operate at room temperature, bypassing the need for complex cooling systems. The most exciting part, we're not just passively observing these phenomena anymore. Breakthroughs in AI and supercomputing allow us to simulate cosmic conditions here on Earth, accelerating discoveries that once took generations. Every unexplained flash in the night sky, every bizarre gravitational anomaly could be the first clue in a chain reaction, leading to technological revolutions we can scarcely imagine today. The universe isn't just showing off its mysteries, it's handing us the tools to build tomorrow. Dark matter isn't just missing mass, it could be the missing piece in our technological evolution. Right now, beneath our feet in massive underground labs and in particle colliders spanning miles, scientists are chasing shadows. They're trying to catch glimpses of particles that might explain this invisible force binding the cosmos together. The wildest part, every failed detection teaches us something new, like how some researchers are repurposing those failures to design ultra-sensitive quantum sensors capable of detecting faint gravitational waves or hidden mineral deposits deep underground. Then there's the energy angle. Dark matter doesn't just interact with gravity. Theoretical models suggest certain types might self-annihilate, releasing pure energy. Startups are already patenting concepts for dark matter reactors that could harness this process, creating power plants with no fuel input and zero emissions. Picture a world where energy scarcity is as outdated as oil lamps, where cities draw power from an invisible grid woven through the fabric of space itself. But the most mind-bending application might be in transportation. If we can isolate dark matter's unique gravitational properties, we could engineer materials that effectively cancel out their own weight. Aerospace engineers speculate this could lead to spacecraft requiring minimal propulsion, just a nudge to break free from Earth's pull, then coasting effortlessly on cosmic tides. Others imagine construction platforms floating skyscrapers into place with anti-gravity cranes. Even medical tech could benefit, with dark matter-inspired devices potentially allowing surgeons to manipulate tissues without physical contact. The race to understand dark matter has already spun off breakthroughs we're using today, those ultra-pure crystals developed for dark matter detectors. They're now improving cancer radiation therapies. The machine learning algorithms created to sift through mountains of collision data, they're optimizing renewable energy grids. Every step into this invisible frontier doesn't just reveal cosmic secrets, it sends ripples through our technological landscape, proving that sometimes the most profound innovations begin by studying what isn't there. Black holes aren't just cosmic vacuum cleaners, they're potential power plants on a scale we can barely comprehend. Picture a singularity so dense it bends the fabric of space-time, spinning at nearly the speed of light while emitting faint whispers of energy known as Hawking radiation. This phenomenon, predicted by Stephen Hawking half a century ago, suggests black holes aren't entirely black, they leak. And that leakage could hold the key to a future where energy scarcity is obsolete. Right now, in labs from Switzerland to California, physicists are recreating black hole conditions using plasma vortices and supercooled quantum fluids. These experiments aren't just academic, they're testing whether we could one day engineer micro black holes no wider than an atom. Such tiny singularities would evaporate almost instantly, converting their entire mass into pure energy via Hawking radiation. The math is staggering. 1 gram of matter transformed this way could release the energy of 1 million nuclear bombs without the fallout. Imagine spacecraft fueled by pinhead-sized black holes, their thrust generated by controlled bursts of radiation, propelling us to Alpha Centauri in years instead of millennia. But the real game changer might be closer to home. Theoretical models suggest orbital power stations could harness energy from naturally occurring black holes, if we find any small enough. These stations would act like cosmic hydroelectric dams, capturing the energy of space-time itself as it swirls toward the event horizon. No combustion, no waste, just the universe's own geometry converted directly into electricity. Some designs even propose using the intense gravitational lensing around black holes to focus solar energy from entire star systems, creating beams of power visible across galaxies. Of course, the challenges are as immense as the opportunities. Containing a man-made black hole would require force fields beyond our current tech, and a single miscalculation could risk an out-of-control singularity. Yet the same was once said of nuclear fission until it became routine. What makes this different is the sheer elegance of the physics. Black hole energy doesn't rely on chemical reactions or even nuclear ones. It taps into the fundamental mechanics of reality, turning the warping of space-time itself into a utility. The implications ripple far beyond energy. Mastery of black hole physics could lead to breakthroughs in material science, with ultra-dense singularity-inspired alloys revolutionizing construction. Or consider medicine. Targeted Hawking radiation might one day destroy tumors with pinpoint accuracy, vaporizing cancer cells without touching healthy tissue. Even computing could leap forward, with black hole analogs helping us crack quantum encryption or simulate entire universes. This isn't about taming monsters, it's about learning their language. Every experiment, every failed containment test, every new equation brings us closer to speaking the universe's most extreme dialect. The day we successfully harness black hole energy won't just mark the end of an era. It'll prove we've graduated from inhabitants of the cosmos to its engineers. Neutrinos might be the universe's ultimate messengers, tiny, ghostly particles so elusive they pass through entire planets like sunlight through glass. Billions stream through your body every second without a trace, making them the perfect candidates for a communication revolution. Unlike radio waves or fiber optics, which get blocked by mountains or oceans, neutrino signals could travel straight through the Earth's core, linking continents instantly. Imagine a future where submarines receive real-time data from command centers without surfacing, or where astronauts on Mars chat with mission control without the agonizing delay of light-speed lag. This isn't just about speed, it's about redefining what connectivity means. Projects like IceCube, a massive detector buried in Antarctic ice, are already decoding neutrino behavior. These particles barely interact with matter, which makes them incredibly hard to detect but also nearly impossible to intercept or jam. That's why militaries and tech giants are eyeing neutrino communication as the gold standard for secure networks. Picture quantum encryption taken to the extreme, where your data isn't just encoded but physically untouchable, beamed directly through the planet's crust. No hackers, no signal degradation, just pure, unfiltered information traveling on cosmic highways. The implications for space exploration are even more staggering. Traditional radio signals weaken over interstellar distances, but neutrinos could carry messages across galaxies with minimal loss. Future probes might send data home via neutrino bursts, allowing us to explore black holes or alien worlds without losing contact. Some theorists even speculate about extraterrestrial civilizations already using neutrino networks. After all, if you wanted to communicate across the cosmos, why rely on anything else? Of course, the challenges are immense. Current neutrino detectors are the size of skyscrapers, and generating a focused neutrino beam requires energies rivaling particle colliders. But remember, the first computers filled rooms too. Breakthroughs in metamaterials and quantum sensors could shrink this tech to practicality, turning today's lab curiosities into tomorrow's smartphones. Already, startups are experimenting with compact neutrino emitters, and NASA has floated concepts for deep space neutrino relays. What makes this so thrilling isn't just the engineering, it's the poetry. Humanity might one day tap into the same shadowy particles born in supernova and cosmic collisions, weaving them into a web linking every corner of existence. The universe has been whispering in neutrinos since the dawn of time. We're finally learning how to listen. Pulsars are nature's most precise timekeepers, cosmic lighthouses, spinning with such regularity they rival our best atomic clocks. These dense neutron stars, remnants of supernova explosions, can rotate hundreds of times per second, sending beams of radiation sweeping across space like the steady tick of a metronome. Their pulses arrive on Earth with staggering consistency, some maintaining accuracy to within 100 trillionths of a second. That level of precision isn't just impressive, it's revolutionary. Right now, NICER mission is proving pulsars aren't just celestial curiosities. By tracking the X-ray flashes from these spinning stars, spacecraft could one day navigate the solar system without relying on Earth-based signals. Imagine a future where ships crossing the asteroid belt or approaching Mars triangulate their position using the steady beats of distant pulsars, creating a galactic GPS that never loses signal. Unlike our current satellite networks, which degrade over interplanetary distances, pulsar navigation would work anywhere in the galaxy, its signals unimpeded by planets or cosmic dust. But the implications go far beyond navigation. Quantum computers, which rely on perfectly synchronized qubits, could use pulsar timings as a universal clock signal. Today's quantum systems struggle with decoherence, their delicate states collapsing if components fall out of sync by even a nanosecond. Pulsars offer a solution. Their immutable rhythms could serve as a backbone for quantum networks spanning planets or even star systems. Financial markets, power grids, and global communications all depend on precise timing. A pulsar-based standard could eliminate microsecond discrepancies that currently cost industries billions. The real magic lies in how these cosmic clocks form. When massive stars collapse, their cores compress into spheres just 12 miles wide yet heavier than our Sun. This incredible density spins magnetic fields trillions of times stronger than Earth's, channeling radiation into beams locked to the star's rotation. The result is a natural timepiece forged in stellar violence, unaffected by terrestrial limitations like temperature fluctuations or mechanical wear. Some pulsars, called millisecond pulsars, have been recycled by stealing matter from companion stars, spinning faster until they achieve near-perfect stability. These ultra-precise variants could become the gold standard for timekeeping across civilizations. There's even speculation that advanced extraterrestrial societies might use pulsar signals as universal reference points, embedding messages in their pulse patterns, a concept that inspired the plaques aboard the Voyager probes. What makes pulsar technology so compelling is its dual nature. It's both ancient and cutting-edge, harnessing processes that began billions of years ago to enable futures we're only beginning to envision. From guiding interstellar probes to securing interplanetary internet, these celestial timekeepers don't just mark the passage of seconds. They might ultimately measure humanity's leap into the cosmos. Quantum entanglement might sound like science fiction, but it's one of the universe's most baffling realities, a phenomenon so strange even Einstein couldn't fully wrap his head around it. Picture two particles born from the same event, separated by light years of empty space. Change one and the other reacts instantaneously, as if they're still touching. This spooky action at a distance, as Einstein famously called it, defies everything we know about speed and distance. Yet today, labs worldwide aren't just observing this cosmic quirk. They're harnessing it to build technologies that could redefine communication, computing, and even transportation. The key lies in quantum teleportation, a process that sounds straight out of Star Trek but is already happening in controlled experiments. Here's how it works when entangled particles are separated. Information about the state of one can be transferred to the other not by sending a signal through space, but by exploiting their invisible connection. Scientists have successfully teleported quantum states across labs, cities, and even between satellites in orbit. The record currently stands at over 1,000 kilometers, with photons beaming their properties across China's MISHUS satellite network. This isn't teleporting matter yet, but it's the foundational step toward transmitting complex information, or even objects, without crossing the distance in between. Now imagine scaling this up. What if we could entangle not just particles, but entire atoms or molecules? The implications are staggering. Secure communications could become unhackable, with encryption keys transmitted via entangled pairs that collapse if intercepted. Quantum internet prototypes are already testing this, creating networks where data travels faster than light, or more accurately, skips the traveling part entirely. But the real game changer could be macroscopic teleportation. While teleporting a person remains firmly in the realm of speculation, researchers are exploring how to entangle larger and larger systems. Some propose using quantum links to transmit the exact state of materials, effectively printing objects at a distance by reconstructing them atom by atom. Of course, the challenges are as immense as the possibilities. Maintaining entanglement with larger objects requires shielding them from even the slightest disturbance. A single stray photon can unravel the connection. And while we can teleport quantum states, the original particle isn't physically moving. Its information is being recreated elsewhere, meaning the sender's version is destroyed in the process. For now, that rules out Star Trek's seamless transporter beams, but breakthroughs in quantum error correction and memory storage are inching us closer to practical applications. The most tantalizing possibility: quantum entanglement might not be limited to human-made systems. Some theorists speculate that the universe itself could be threaded with ancient entanglement left over from the Big Bang, a cosmic web of invisible connections waiting to be tapped. If true, mastering this phenomenon wouldn't just revolutionize technology. It would mean unlocking a hidden layer of reality, one where distance is an illusion and the universe operates as a single, interconnected whole. From ultra-secure networks to instant data transfer across planets, entanglement isn't just a laboratory curiosity. It's a glimpse into a future where the rules of space and time don't apply as we know them. Every experiment, every successful teleportation of a quantum state brings us closer to bending those rules to our advantage. The day we fully harness this spooky force won't just mark a leap in technology. It'll prove that the universe's strangest behaviors might be its most useful gifts. Cosmic rays are more than just space radiation. They're high-speed messengers from the most violent events in the universe. These charged particles, mostly protons and atomic nuclei, race through space at nearly the speed of light, some carrying energies millions of times greater than anything our most powerful particle accelerators can produce. They originate from supernova explosions, colliding neutron stars, and possibly even supermassive black holes, making them natural laboratories for physics we can't recreate on Earth. When these particles slam into our atmosphere, they create cascades of secondary particles, a phenomenon that's not just fascinating but packed with technological potential. One of the most immediate applications lies in radiation shielding. Astronauts on long-duration missions, like a trip to Mars, would face constant bombardment from cosmic rays that can damage DNA and electronics. By studying how these particles interact with matter, scientists are developing new materials that could block or redirect harmful radiation. Some experiments focus on metamaterials with microscopic structures designed to scatter incoming particles, while others explore biological solutions like genetically engineered microbes that repair radiation damage in human cells. The International Space Station is currently testing various shielding prototypes, some inspired by cosmic ray interactions with planetary magnetic fields. But the real game changer might be in energy production. The most energetic cosmic rays pack a punch equivalent to a fast-pitched baseball, all concentrated into a single subatomic particle. If we could understand and replicate the cosmic accelerators that produce these extreme energies, we might unlock new methods of power generation. Some theoretical designs suggest using artificial magnetic fields, modeled after those found around neutron stars, to create compact particle accelerators no larger than a shipping container. These could revolutionize medicine by making cancer treatments more accessible or enable clean nuclear fusion by pre-accelerating fuel particles before injection into plasma reactors. Then there's the exotic matter angle. Certain cosmic rays appear to contain strangelets, hypothetical particles made of strange quarks that don't exist in normal matter. If harnessed, these could lead to materials with unbelievable properties, superconductors that work at room temperature, ultra-dense alloys for space construction, or even stable forms of antimatter. Labs like CERN are already attempting to create and study strange matter in controlled conditions, using cosmic ray data as their guidebook. What makes cosmic rays so valuable is their dual role as both tools and teachers. Every particle that reaches Earth carries information about the extreme environments that created it, while simultaneously challenging our understanding of physics. From improving semiconductor designs to inspiring next-generation propulsion systems, these invisible space travelers might hold the blueprint for technologies we haven't even named yet. The universe isn't just sending us random radiation. It's delivering concentrated packets of possibility, each one a clue waiting to be decoded. The atmospheres of distant exoplanets aren't just scientific curiosities, they're cosmic cheat codes for rewriting the rules of habitability. Take TRAPPIST-1e, a rocky world orbiting a star 40 light-years away, shrouded in an atmosphere that might contain traces of oxygen, carbon dioxide, or even water vapor. While we can't yet breathe its air or feel its winds, this alien sky holds something far more valuable, a blueprint. Every molecule swirling above its surface could teach us how to engineer Earth-like conditions where none exist naturally. The key lies in synthetic biology, where scientists are already designing microbes capable of converting toxic gases into breathable air, inspired by the chemical cocktails found on worlds like TRAPPIST-1e. Imagine microscopic terraformers, custom-engineered organisms seeded into the rusty soil of Mars, slowly churning its thin carbon dioxide atmosphere into oxygen-rich air. These biological machines wouldn't just mimic Earth's natural processes, they'd optimize them using exoplanet data to skip millions of years of trial and error. Some experimental strains can already survive Martian soil simulations, metabolizing perchlorates and releasing usable nitrogen. Others, modeled after hypothetical organisms that might thrive in TRAPPIST-1e's high radiation environment, could shield crops under domes by absorbing harmful cosmic rays. The same techniques might even help us rebalance Earth's climate, with algae blooms engineered to sequester carbon at oceanic scales, their designs refined by studying gas cycles on planets with runaway greenhouse effects. But the real breakthrough isn't just copying alien atmospheres, it's remixing them. Venus, with its crushing CO2 blanket, and Titan, drowning in methane, prove that habitability isn't one size fits all. By cataloging atmospheric recipes from hundreds of exoplanets, we're compiling a cosmic cookbook for planetary engineering. Some combinations could unlock shortcuts. A whiff of ammonia might accelerate cloud formation to cool an overheating world, while trace sulfur compounds could stabilize temperatures on a tidally locked planet. There's even speculation about photosynthesis 2.0, using exotic pigments adapted to dim red dwarf suns, turning low-energy light into viable crops for future Martian colonies. The implications stretch far beyond our solar system. If we master atmospheric design here, future generations could transform frozen moons or barren asteroids into way stations for interstellar travel. Picture relay stations dotting the galaxy, each with a breathable bubble grown from local materials and tuned to the chemistry of its host world. The technology to do this isn't locked in some distant future. It's being prototyped today in labs combining astrobiology with CRISPR breakthroughs. Every new exoplanet atmosphere we analyze adds another tool to our toolkit, another page to the manual on how to turn dead rock into living space. What makes this more than science fiction is the urgency behind it. Climate change has shown how fragile Earth's balance really is, while exoplanet studies reveal how many ways that balance can fail. By learning to rebuild atmospheres from scratch, we're not just preparing to colonize Mars, we're ensuring ourselves against existential threats. The same microbes that might one day green the red planet could already be helping reefs survive acidifying oceans or cities endure smog-filled skies. The universe has provided countless examples of what works and what doesn't in planetary atmospheres. Our job isn't just to observe them, but to learn their secrets and start writing our own. Dark energy isn't just stretching the universe apart. It might hold the secret to folding space itself. Picture this: the same invisible force accelerating galaxies away from each other could one day power engines that compress the fabric of reality ahead of a spacecraft while expanding it behind, creating a warp bubble that moves faster than light without breaking physics. The concept, first proposed by physicist Miguel Alcubierre in the 90s, sounded like pure fantasy. But today, researchers are discovering that dark energy's repulsive gravity might be the missing ingredient to make it work. The math is tantalizing. Dark energy accounts for nearly 70% of the universe's total energy, yet we still don't know what it truly is. What we do know is that it counteracts gravity on cosmic scales, pushing galaxies apart at ever-increasing speeds. If we could replicate that effect locally, creating a pocket of negative energy density, we might engineer a warp drive that bends space-time around a ship instead of pushing it through. NASA Eagleworks Lab has already tested miniature versions of this idea using metamaterials, artificial structures designed to manipulate electromagnetic fields in ways that mimic space-time warping. Early results suggest it's not impossible, just unimaginably difficult. Here's where it gets wild. Some theories suggest dark energy might be linked to quantum vacuum fluctuations, tiny particles constantly popping in and out of existence. If we could somehow amplify or direct those fluctuations, we might create the conditions needed for an Alcubierre drive. Experiments with Casimir cavities, devices that measure the pressure of these quantum fluctuations, are hinting at ways to manipulate this energy. Imagine a spacecraft surrounded by a ring of exotic matter generating a controlled dark energy field, effectively surfing a wave of compressed space-time. No G-forces, no fuel constraints, just the universe itself rearranging to carry you forward. Of course, the hurdles are cosmic in scale. Stabilizing a warp bubble would require energies comparable to converting Jupiter's entire mass into pure energy far beyond our current capabilities. There's also the problem of causality violations. Faster-than-light travel could theoretically allow time travel, creating paradoxes that make physicists shudder. But breakthroughs in quantum field theory and metamaterials are chipping away at these barriers. Startups like Applied Physics are already working on scaled-down warp field interferometers, while academic teams explore how to reduce the energy requirements using layered spacetime geometries. The implications stretch far beyond interstellar travel. Mastering dark energy could revolutionize energy production, offering clean power drawn from the vacuum of space itself. Or consider construction. Materials engineered with dark energy analogs might self-assemble or levitate effortlessly. Even medicine could benefit, with dark energy-inspired tech enabling non-invasive surgeries that manipulate tissues at a distance. This isn't about chasing starships, it's about rewriting our relationship with space and time. Every experiment, every theoretical tweak brings us closer to a future where the universe's most mysterious force becomes its most useful tool. The day we harness dark energy won't just open the galaxy to exploration. It'll prove that the cosmos has been handing us the keys all along. We just needed to learn how to turn them. The Fermi paradox isn't just a cosmic riddle, it's a mirror reflecting humanity's future. If the universe truly brims with life, as calculations suggest, then the eerie silence surrounding us could mean one of two things. Either intelligent civilizations are vanishing before they can spread, or they've evolved beyond our current methods of detection. Both possibilities are equally terrifying and electrifying. Consider the Great Filter theory, which suggests some catastrophic event prevents civilizations from reaching interstellar travel. If true, identifying that filter could be our only chance to avoid it. But flip the script, and the paradox becomes a goldmine of inspiration. What if advanced societies don't broadcast radio waves or build obvious megastructures? What if they've moved beyond visible technology entirely? Take Dyson spheres, hypothetical structures that encase stars to harvest their energy. While we've yet to spot one, the search has led to breakthroughs in solar collection and energy storage here on Earth. Projects like Starshade's massive space-based disks designed to block starlight were originally conceived to spot alien megastructures. Now, they're helping astronomers study exoplanet atmospheres with unprecedented clarity. Even the hunt for extraterrestrial signals has supercharged our AI, with machine learning algorithms trained to sift through petabytes of radio noise, now detecting everything from rare pulsars to early signs of supernova. Then there's the neutrino angle. If advanced civilizations communicate via these ghostly particles, as some theorists propose, our efforts to detect them are already revolutionizing quantum computing and medical imaging. The same detectors built to catch cosmic neutrinos are being adapted to scan for brain tumors with pinpoint accuracy. And while we're peering into the darkness, we're also learning how to hide. The study of cloaking technologies, once the realm of UFO conspiracy theories, has given rise to metamaterials that bend light around objects, with applications ranging from stealth aircraft to earthquake-resistant buildings. The paradox's deepest lesson might be about sustainability. If most civilizations burn out quickly, the survivors could be those who master energy efficiency and environmental harmony. That's why initiatives like zero-waste fusion reactors and closed-loop ecosystems aren't just eco-friendly, they might be existential necessities. The silent cosmos isn't just a warning, it's a challenge. Every technology we develop to search for others doubles as a tool to ensure we'll still be here when they finally call back. So while the stars remain quiet for now, they're far from silent. They're whispering the blueprints for our survival if we're willing to listen. The Kardashev scale isn't just a ranking of civilizations, it's a survival guide written in the language of energy. Imagine a future where humanity doesn't just live on Earth but harnesses the full output of its winds, tides, and sunlight, a Type 1 civilization. That's just the starting point. To reach Type 2, we'd need to capture all the energy of our Sun, perhaps by building a Dyson swarm of orbiting solar collectors. And Type 3, that's controlling the power of entire galaxies. Right now, we're barely a Type 0.7, still tethered to fossil fuels like a child clinging to training wheels. But the projects taking shape today, fusion reactors mimicking stars, solar satellites beaming energy to Earth, even early plans for asteroid mining are the first wobbling steps toward walking among the cosmic giants. Take Japan's SSPS initiative, aiming to launch solar panels into orbit where sunlight is 8 times stronger than on Earth's surface. These panels would wirelessly transmit energy back as microwaves, turning the sky itself into a power grid. Or consider ITER, the International Fusion Project, where scientists are literally building a miniature star in southern France, replicating the process that lights the universe. These aren't just engineering feats, they're evolutionary leaps, each one nudging us closer to becoming a true Type 1 civilization. But energy isn't the only hurdle. The Kardashev scale also measures something deeper, a civilization's ability to manage complexity. To reach Type 1, we'll need global cooperation on an unprecedented scale. No easy feat when nations still squabble over borders and resources. That's why projects like the Artemis Accords matter. This international agreement for peaceful lunar exploration proves we're starting to think like a planetary civilization, not just competing tribes. The scale's creator, Nikolai Kardashev, originally imagined it as a way to classify potential extraterrestrial signals, yet its real power lies in holding up a mirror to humanity. Every watt of clean energy we generate, every sustainable city we build, every asteroid we mine for resources instead of stripping our planet, these aren't just technological wins. They're proof we're learning to think like a civilization that plans to stick around. The universe doesn't reward hoarders, it rewards those who harness energy wisely and expand without consuming their own future. Some argue the scale is too narrow, focusing only on energy while ignoring culture or wisdom. But perhaps that's the point. Energy isn't just about power, it's about possibility. The difference between a Type 0 and Type 1 civilization isn't just stronger machines. It's the freedom to redirect hurricanes before they make landfall, to end hunger by precision growing food anywhere on Earth, to heal ecosystems with targeted climate engineering. The scale isn't pushing us toward domination, but toward responsibility. The most exciting part, we're closer than we think. With advances in AI, nanotechnology, and quantum computing, the tools to manage planetary scale systems are falling into place. Private companies are already plotting solar farms in space, while governments invest in fusion breakthroughs. The dream isn't to become overlords of energy, but custodians using the universe's gifts to ensure no child goes hungry, no species vanishes needlessly, and no disaster goes unprevented. That's the real promise of the Kardashev scale, not just surviving among the stars, but deserving to. Amuamua wasn't just another space rock. It was our first confirmed visitor from another star system, and it defied every expectation. When this mysterious object streaked through our solar system in 2017, it left scientists scratching their heads. Its elongated shape, unlike any natural asteroid we'd seen, combined with its inexplicable acceleration as it moved away from the sun, sparked a firestorm of speculation. Was it a fragment of a shattered planet, a comet without visible outgassing, or, as some daring theorists proposed, could it have been an artifact of intelligent design, a light sail propelled by starlight, sent from a civilization far beyond our own? The truth might be stranger than fiction. While most researchers lean toward natural explanations, like hydrogen ice sublimation giving it an unexpected push, the mere possibility of artificial origins sent shockwaves through the scientific community. That slim chance was enough to reframe how we think about interstellar travel. Enter Breakthrough Starshot, an audacious project aiming to launch a fleet of gram-scale nanoprobes to Alpha Centauri within our lifetime. These tiny spacecraft, equipped with reflective light sails, would be propelled by powerful ground-based lasers, reaching 20% the speed of light, a concept directly inspired by the Amuamua debate. But the real lesson of Amuamua isn't just about propulsion, it's about perspective. For the first time, we held tangible proof that interstellar objects regularly pass through our cosmic neighborhood. Some estimates suggest there could be thousands like it drifting unseen through our solar system at any given moment. That realization has sparked a new era of sky surveys, with telescopes like the Vera Rubin Observatory preparing to scan the heavens for more of these enigmatic travelers. Every one we find could be a Rosetta Stone for understanding planetary formation in alien star systems, or even a carrier of exotic materials unlike anything in our solar system. The implications stretch far beyond astronomy. If Amuamua was natural, studying its composition could reveal how common Earth-like planets are in the galaxy. If it was artificial, well, that would rewrite history. Either way, its brief visit was a cosmic wake-up call, reminding us that the universe is far more dynamic and unpredictable than we often assume. Projects like Starshot, along with next-generation observatories, are our way of answering that call. Not just waiting for the next interstellar visitor, but actively reaching out to meet it. What makes Amuamua so thrilling isn't just the mystery of what it was, but what it represents, a glimpse into the vast, uncharted possibilities of interstellar space. Whether it was a weirdly shaped rock or something more, its legacy is already reshaping our ambitions, proving that sometimes the most profound discoveries come from the things that don't quite fit. The next time an object like this appears, we'll be ready not just to watch it pass, but to chase it down and learn its secrets. After all, the universe has a habit of surprising those who dare to look closer. Time dilation isn't just a quirk of physics, it's a doorway to the stars. Picture a spacecraft accelerating to near light speed, where time itself bends to the will of relativity. For astronauts on board, years might pass while decades slip by on Earth, a challenge for human connections but an opportunity for interstellar travel. This isn't hypothetical. Atomic clocks aboard the International Space Station already tick slightly faster than their Earth-bound counterparts, proving Einstein right down to the nanosecond. But what if we could control this effect intentionally? Enter the concept of artificial gravity wells. Just as massive objects like black holes warp spacetime, theoretical constructs called Alcubierre shells could mimic this effect on demand. These hypothetical structures would generate intense gravitational fields around a spacecraft, effectively creating a localized time bubble where clocks slow dramatically relative to the outside universe. Passengers might experience a 6-month journey to Alpha Centauri, while 50 years pass back home, not ideal for round trips, but revolutionary for one-way colonization missions. Experiments with Bose-Einstein condensates are already demonstrating how extreme cold can slow atomic vibrations, offering clues about manipulating time's flow at larger scales. The implications go far beyond travel. Imagine medical pods where critically injured patients could be placed in time suspension, slowing their biological processes until proper treatment arrives. Or consider deep space communication networks utilizing time-dilated relay stations to compensate for the agonizing delays of interstellar distances. Even planetary defense could benefit. Asteroids on collision courses might be intercepted by drones operating in altered timeframes, where hours of human decision-making translate to microseconds in real space. The true breakthrough might come from an unexpected direction: quantum entanglement. Recent experiments show entangled particles can exhibit synchronized time dilation effects across vast distances. If scalable, this could lead to time-locked navigation systems where spacecraft adjust their temporal flow to stay synchronized with Earth's clocks, eliminating the disorienting effects of relativistic travel. Of course, the energy requirements remain astronomical. Warping spacetime demands pressures rivaling neutron stars, and containing such forces without tearing the fabric of reality is no small feat. Yet every year brings us closer, from improved gravitational wave detectors mapping spacetime's flexibility to metamaterials that bend light in ways analogous to time dilation. The universe has already shown us the blueprint. Now we're learning how to trace its lines. What makes this pursuit so compelling isn't just the promise of star travel, but the deeper revelation it brings. Time isn't some universal metronome, it's a malleable dimension, as open to engineering as steel or silicon. The day we master its manipulation won't just change how we explore space. It'll redefine what it means to exist within it. White holes stand as one of the most tantalizing what-ifs in theoretical physics: cosmic fountains where space-time itself reverses its flow. Picture a black hole running backward in time. Instead of swallowing everything that crosses its event horizon, a white hole would violently expel matter and energy, like a cosmic fire hose blasting particles into existence. The mathematics of general relativity allow for such objects, though we've never observed one. Yet the mere possibility rewrites our understanding of cosmic resource cycles. Consider the implications if we found one. Unlike black holes, which trap even light, white holes would radiate energy so fiercely they could outshine entire galaxies. Some models suggest they might be the other end of black holes, connected by wormholes, meaning matter consumed by a black hole in one location could emerge from a white hole elsewhere in the universe. This isn't just interstellar travel. It's matter recycling on a universal scale. Imagine spacecraft designed to ride these cosmic currents, or industrial platforms orbiting white holes to harvest their boundless energy. Entire civilizations might thrive by tapping into these natural particle accelerators, drawing from what could essentially be the universe's reset button. The challenges are as staggering as the possibilities. White holes would likely be unstable, their explosive energy output causing them to self-destruct unless somehow stabilized, perhaps by advanced civilizations mastering space-time engineering. Even detecting one would require rethinking astrophysics, as their signatures could mimic quasars or other high-energy phenomena. Yet the hunt itself pushes science forward. Projects like the Laser Interferometer Gravitational Wave Observatory, originally built to detect black hole collisions, are now searching for anomalies that might hint at white hole activity. What makes white holes so compelling isn't just their theoretical power source, it's the philosophical shift they demand. If matter and energy can be endlessly recycled through these cosmic portals, the universe might operate more like a self-sustaining organism than a one-way expansion. Civilizations that harness this process wouldn't just be tapping into a resource, they'd be joining the universe's own metabolic cycle, aligning technology with the deepest rhythms of existence. While white holes remain mathematical phantoms for now, they represent the ultimate test of human ingenuity. To prove their existence would require rewriting textbooks. To utilize them would mean bending physics to our will, and that's the real lesson here. The universe's greatest mysteries aren't just puzzles to solve, but invitations to evolve. Whether white holes are real or not, the act of searching for them is already stretching the boundaries of what we believe is possible. Multiverse theory isn't just a wild thought experiment. It could be the ultimate sandbox for technological breakthroughs. Imagine an infinite tapestry of parallel realities, each with its own laws of physics, its own evolutionary paths for civilizations, its own versions of technology we can't even conceptualize. While we haven't proven their existence, the very idea is reshaping how we approach innovation here in our universe. Quantum computing, for instance, borrows from multiverse logic, its qubits effectively, testing countless possibilities simultaneously, as if tapping into alternate realities to find solutions faster than any classical computer ever could. Some of the most cutting-edge research in physics today stems from this cosmic what if. Take dark matter detectors buried deep underground, originally designed to find particles from other dimensions. Though they haven't caught a whiff of parallel universes yet, their ultra-sensitive designs are now being adapted to detect early-stage cancers or hidden mineral deposits with astonishing precision. Even the Large Hadron Collider, while smashing protons to uncover the universe's basic building blocks, could inadvertently reveal signatures of higher dimensions predicted by string theory. Every experiment built to chase multiversal ghosts ends up gifting us tools that transform our own world. The real magic lies in how this theory reframes failure. In a multiverse, every dead-end experiment here might represent a thriving technology elsewhere, so why not try the impossible? Startups are already running with this mindset, testing radical energy concepts like vacuum energy extraction or negative mass propulsion, ideas that sound like pure fantasy but follow logically from alternate physics models. Universities have launched multiverse simulation projects, not to prove parallel worlds exist, but to stress test our own tech against infinite hypothetical scenarios. The result: more resilient AI, more adaptable infrastructure, and a generation of engineers trained to think in possibilities rather than limitations. Perhaps most intriguing are the hypothetical civilizations that might inhabit these other universes. A reality with stronger nuclear forces could host species that mastered fusion power as easily as we harnessed steam. A universe where time flows backward might have engineers who uninvent technologies to solve problems. While we'll likely never meet these beings, their theoretical existence pushes us to ask, if they cracked interstellar travel or unlimited clean energy, how did they do it? That question alone has spawned entire fields of speculative physics, with papers on cosmic archaeology, reverse engineering tech that might exist somewhere in the multiverse's infinite variations. Skeptics argue this is all science fiction, and they're partly right. But history shows that today's fiction often becomes tomorrow's foundation. The same math that describes parallel universes also underpins quantum encryption. The same equations that model alternate dimensions help predict material properties for next-gen solar cells. Whether the multiverse is real or not, treating it as a theoretical playground has given us something far more valuable than answers. It's taught us how to ask better questions. Every time we entertain an idea that seems too strange to be true, we're not just exploring the cosmos, we're expanding the boundaries of what's possible right here, right now. Neutron stars are cosmic alchemists, forging matter under conditions so extreme they defy imagination. Picture a celestial object so dense that a single teaspoon of its material would weigh more than Mount Everest, a place where atoms are crushed into a sea of neutrons packed tighter than sardines in a can. These stellar remnants, born from the explosive deaths of massive stars, aren't just fascinating oddities. They're natural laboratories for physics we can't recreate on Earth, offering a backstage pass to the universe's most extreme material science. Take their crusts, for instance. The surface of a neutron star is a crystalline lattice of iron nuclei squeezed so tightly that electrons fuse with protons, forming a neutron-rich material with the strength of steel but a fraction of the size. Scientists call this nuclear pasta, not just for its whimsical name, but because it behaves like a cosmic version of reinforced concrete. Studying these structures through gravitational wave observatories like LIGO, which detects ripples in spacetime when neutron stars collide, could unlock the secret to ultra-strong, lightweight materials here on Earth. Imagine skyscrapers built with neutron star-inspired alloys, or spacecraft hulls thin as paper yet tougher than diamond. Then there's the energy potential. Neutron stars spin at dizzying speeds, some rotating hundreds of times per second, their magnetic fields trillions of times stronger than Earth's. These fields are so intense they twist the fabric of space itself, creating conditions where matter and energy blur together. Researchers are already exploring how to mimic these magnetic dynamics in compact fusion reactors, using principles gleaned from neutron star physics to contain superheated plasma more efficiently. The goal: power plants no larger than a shipping container, fueled by the same processes that light up these cosmic beacons. But the real game changer lies deeper still. At the core of a neutron star, matter might dissolve into a soup of quarks, the fundamental building blocks of protons and neutrons. This quark-gluon plasma is a state of matter so exotic it hasn't existed naturally since the first microseconds after the Big Bang. Laboratories like CERN are smashing heavy ions together to recreate these conditions, hoping to uncover new forms of matter that could revolutionize energy storage. A single gram of stable quark matter, if we could produce it, might store enough energy to power a city for years. The beauty of neutron star research isn't just in its far future applications. Every collision observed by LIGO, every pulse detected by radio telescopes, chips away at the boundaries of what we know. From ultra-precise atomic clocks calibrated to pulsar rhythms to quantum computers leveraging neutron star-like entanglement, these cosmic extremes are already shaping our technology. They remind us that the universe doesn't just hold mysteries, it holds blueprints, and sometimes the key to tomorrow's breakthroughs is written in the death throes of a star. Gamma-ray bursts are the universe's most violent fireworks, cosmic detonations so powerful they release more energy in a few seconds than our sun will emit in its entire lifetime. These fleeting flashes, often originating from collapsing stars or colliding neutron stars billions of light years away, illuminate the darkest corners of space with light 1,000,000 trillion times brighter than our sun. But beyond their awe-inspiring spectacle, they hold a tantalizing promise, the key to unlocking energy sources beyond our wildest dreams. The numbers alone are staggering. A single gamma-ray burst can unleash as much energy as our entire galaxy emits over the same duration. If we could capture even a fraction of that output, say, the energy from 1 millisecond of a burst, it could power human civilization for centuries. The challenge, of course, is that these events are unpredictable, fleeting, and catastrophically destructive up close, but that hasn't stopped scientists from dreaming. Some theorize about advanced civilizations using gamma-ray bursts as natural particle accelerators, harvesting their relativistic jets to forge exotic matter or propel interstellar missions. Others speculate about burst mining, where future technologies might siphon energy from these events by intercepting their afterglows across interstellar distances. What makes gamma-ray bursts so fascinating isn't just their raw power, it's what they reveal about the extremes of physics. These explosions generate magnetic fields so intense they twist space itself, accelerating particles to velocities just shy of light speed. Laboratories like CERN can only dream of replicating such conditions, yet nature performs these experiments routinely in distant galaxies. By studying the afterglows of these bursts, we're uncovering clues about how matter behaves under pressures and temperatures that make the core of a hydrogen bomb seem tame. Already, insights from gamma-ray astronomy are inspiring new approaches to fusion containment, with researchers mimicking the magnetic turbulence of these cosmic explosions to stabilize plasma here on Earth. Then there's the puzzle of their origins. Some bursts arise from hypernova-supernova on steroids, while others erupt when neutron stars spiral into black holes, spinning up jets of energy so focused they could drill through planets. Understanding these mechanisms isn't just academic. It's teaching us how to manipulate energy on scales we once thought impossible. Projects like the Einstein Telescope, a next-generation gravitational wave observatory, aim to catch these events in the act, combining gamma-ray data with ripples in spacetime to map the physics of these cosmic power plants. The real breakthrough might come from an unexpected direction. Gamma-ray bursts could be nature's ultimate warning system. Their relativistic jets are so precise that if one were pointed at Earth, even from thousands of light years away, it could strip our ozone layer and trigger mass extinctions. But by learning to predict and track these events, we might one day engineer shields, perhaps atmospheric scattering satellites or magnetic deflectors, to neutralize their threat. The same research could protect future interstellar travelers or even help us redirect burst energy for peaceful use, turning existential risks into cosmic utilities. What makes these bursts more than just celestial curiosities is their duality. They're both destroyers and teachers, offering glimpses into physics frontiers while reminding us how small we are in the cosmos. Every time a new burst flickers on our telescopes, it's not just a distant explosion, it's a message. One that says the universe's most violent events might hold the very tools we need to survive them. Vacuum energy isn't empty at all, it's a seething quantum ocean where particles flicker in and out of existence so fast we can't detect them. This zero-point energy, the lowest possible state of a quantum system, means that even at absolute zero temperature, space itself hums with activity. The numbers are mind-bending. A single cubic centimeter of pure vacuum may contain more energy than all the matter in the observable universe combined. If we could tap even a fraction of this, it would rewrite the rules of civilization. The Casimir effect gives us a tantalizing glimpse of how this might work. When two ultra-smooth metal plates are placed nanometers apart in a vacuum, quantum fluctuations outside the plates exert more pressure than those between them, forcing the plates together. This isn't just a laboratory curiosity, it's proof that vacuum energy can do measurable work. Researchers at institutions like Harvard and Delft University are now engineering nanostructured surfaces to amplify this effect, creating microscopic vacuum engines that could one day power everything from medical implants to satellites. Imagine a world where batteries never die because they draw energy from the fabric of space itself, but the real breakthrough might come from unexpected directions. The same quantum fluctuations that create vacuum energy also appear to play a role in dark energy, the mysterious force accelerating the universe's expansion. Some theorists suggest that mastering zero-point energy could let us manipulate spacetime itself, not just for power generation, but for propulsion. Projects like NASA's Eagleworks Lab have explored theoretical warp drives that would ride quantum vacuum fluctuations like surfers catching a wave, compressing spacetime ahead of a spacecraft while expanding it behind. Of course, the challenges are as immense as the potential. Extracting useful energy from the vacuum violates no laws of physics, but doing so efficiently requires technologies we've barely begun to imagine. Early prototypes face hurdles like quantum decoherence and the staggering energy costs of creating the necessary conditions. Yet every failed experiment teaches us something new. The same nanoscale materials developed for vacuum energy research are already improving solar cell efficiency and quantum computing. What makes this pursuit so compelling isn't just the promise of limitless energy, it's the philosophical shift it demands. We're used to thinking of empty space as nothingness, but quantum physics paints a different picture. The void is alive, crackling with potential. The day we learn to harness it won't just solve our energy crisis. It'll prove that the greatest power source wasn't in stars or atoms all along, but in the infinite expanse between them. Wormholes aren't just science fiction, they're cosmic backdoors written into the very fabric of reality. Einstein's equations revealed that spacetime isn't a rigid stage but a flexible sheet that can fold, twist, and even tear under extreme conditions. These hypothetical tunnels, connecting distant points in the universe, could theoretically let us traverse galactic distances in the blink of an eye. The catch, keeping a wormhole stable, requires something called exotic matter, a substance with negative energy density that defies normal physics by pushing space outward rather than pulling inward. While we've never observed such matter, quantum experiments with Casimir vacuums and metamaterials hint that it might not be impossible to create. The real value of wormhole research isn't just about building stargates, it's about stress testing our understanding of physics. Every paper published on traversable wormholes forces scientists to reconcile general relativity with quantum mechanics, two frameworks that famously refuse to play nice. Take the AR equals EPR conjecture, a bold idea suggesting that entangled particles might be connected by microscopic wormholes. This isn't just poetic symmetry, it's a potential roadmap for unifying gravity with quantum theory. Laboratories studying quantum entanglement are already borrowing from wormhole mathematics to develop ultra-secure communication networks, proving that even theoretical physics can have down-to-earth applications. Then there's the engineering angle. While a galaxy-spanning wormhole remains fantasy, scaled-down versions could revolutionize space travel within our solar system. Imagine quantum bridges between Earth and Mars, stabilized by rings of lab-grown exotic matter, allowing supply shipments to bypass orbital mechanics entirely. The energy requirements would be astronomical, literally, but breakthroughs in vacuum energy and dark matter research might one day provide the needed power source. Some models even suggest naturally occurring wormholes could be hiding in plain sight, disguised as pulsars or black holes, waiting for us to develop the tools to identify and stabilize them. What makes wormholes so compelling is their duality. They're both a destination and a journey, a theoretical playground where today's calculations become tomorrow's breakthroughs. The mathematics that describe them are already improving gravitational wave detectors and inspiring new approaches to quantum computing. Whether we ever build a functioning wormhole or not, the act of trying is expanding the boundaries of human ingenuity. After all, the universe didn't give us the laws of physics to limit us, but to challenge us to rewrite them. Astrobiology isn't just about finding life in space. It's about letting alien survival strategies rewrite our engineering playbook. Take tardigrades, those microscopic water bears that can survive the vacuum of space, blistering radiation, and temperatures near absolute zero. Their secret. a sugar called trehalose that forms a glass-like shield around their cells, preserving vital structures until conditions improve. Scientists are already mimicking this trick to develop revolutionary preservation techniques. Imagine vaccines stabilized at room temperature for years, or organs kept viable for transplant during long space missions. But the real game changer lies in agriculture. By splicing tardigrade DNA into crops, researchers are creating plants that withstand drought and radiation, potentially securing food supplies on Mars or in a climate-changed Earth. Then there's Deinococcus radiodurans, a bacterium so resistant to radiation it's nicknamed Conan the Bacterium. While a human would die after absorbing 10 grays of radiation, this microbe shrugs off 15,000. Its superpower, a rapid DNA repair system that stitches its genetic code back together like a molecular sewing machine. Labs are now reverse engineering this process to develop self-healing materials, plastics that seal their own cracks, electronics that repair fried circuits, even concrete infrastructure that patches its own fractures after earthquakes. The European Space Agency has experimented with embedding similar bacterial spores in spacecraft coatings, creating hulls that sweat calcium carbonate to seal micrometeorite punctures automatically. But extremophiles offer more than just durability hacks. The sulfur-loving microbes thriving in Yellowstone's boiling acid pools have inspired new battery chemistries that operate in extreme heat. Organisms from Antarctica's blood-red brine lakes, where salt concentrations would pickle most life, are teaching us how to design anti-freeze proteins for cryogenic storage. Even the humble lichen, which survives Martian-like conditions in Earth's high deserts, has become the blueprint for living paints that generate oxygen while absorbing carbon dioxide, potentially turning future Martian habitats into self-sustaining ecosystems. What makes these discoveries so transformative isn't just their immediate applications, it's the shift in perspective they demand. For centuries, we've treated space as a dead zone to be conquered with brute force engineering. Astrobiology suggests a smarter approach. Instead of fighting hostile environments, we can borrow the tools of creatures who have already mastered them. The same evolutionary innovations that let life cling to existence in volcanic vents or polar ice might one day let our technology thrive in asteroid belts or on scorching exoplanets. The ultimate lesson: life isn't fragile, it's ingenious. By studying how organisms survive cosmic extremes, we're not just preparing to explore space. We're learning how to partner with it, turning the universe's harshest corners into places we can call home. Solar sails represent one of the most elegant solutions to interstellar travel. No rockets, no fuel, just the gentle but relentless push of starlight itself. Picture vast, gossamer thin mirrors unfurling in space, catching photons from the sun like cosmic winds filling a ship's sails. The concept isn't science fiction anymore. Light Sail 2, a crowd-funded mission by the Planetary Society, has already proven the technology works, maneuvering in Earth's orbit using nothing but sunlight. But this is just the beginning. Imagine scaling that idea up with advanced metamaterials, engineered surfaces thinner than a human hair yet stronger than steel, capable of reflecting or absorbing specific wavelengths of light with pinpoint precision. The potential here is staggering. Traditional propulsion systems hit a hard limit with the rocket equation. The more fuel you carry, the more fuel you need to lift that fuel. Solar sails break that cycle entirely. Once deployed, they accelerate continuously, their speed limited only by the sail's size and the patience of mission planners. A sail the size of a football field, propelled by a powerful ground-based laser, could reach Alpha Centauri in just decades instead of millennia. breakthrough Starshot, an initiative backed by Stephen Hawking and Yuri Milner, aims to do exactly that, sending gram-scale probes to our nearest stellar neighbor at 20% the speed of light. But the real magic lies in the materials. Modern sails rely on reflective aluminum or mylar, but future versions could incorporate self-healing polymers that repair micrometeorite damage or smart coatings that adjust their reflectivity to optimize thrust. Some designs even propose embedding quantum dots to convert high-energy photons into additional momentum, effectively turbocharging the sail's acceleration. And then there's the ultimate dream, harnessing not just sunlight, but the focused beams of orbiting lasers or even the intense radiation from neutron stars, turning the entire galaxy into a network of cosmic highways. The implications stretch far beyond exploration. Solar sails could revolutionize how we maintain satellites, allowing them to keep indefinitely without fuel. They might enable rapid response missions to asteroids on collision courses with Earth or serve as interstellar communication relays, beaming data back from probes venturing into the abyss. There's even speculation about using them for slow but steady generational ships, their enormous sails doubling as solar panels to power habitats during centuries-long voyages. What makes solar sails so compelling isn't just their efficiency, it's their humility. They don't fight the universe's rules, they embrace them, riding forces that have existed since the first stars ignited. Every photon that bounces off a sail is a reminder that the cosmos isn't just a backdrop for human ambition, it's an active participant, waiting for us to learn its rhythms. The day we truly master this technology won't just mark a leap in engineering. It'll prove that sometimes the best way to move forward is to let go and let the light carry us. Cosmic inflation isn't just a theory about the universe's birth, it's the ultimate power source hidden in plain sight. Picture the first trillionth of a second after the Big Bang, when space itself expanded faster than light, stretching quantum fluctuations into the seeds of galaxies. This wasn't just a one-time event, it left fingerprints in the cosmic microwave background, the afterglow of creation that still permeates the cosmos. But here's the mind-blowing part. If we could decipher how inflation worked, we might not just understand the universe's origins, we could learn to manipulate the fabric of reality on demand. The clues are etched in the sky. Satellite missions like Planck have mapped the cosmic microwave background with staggering precision, revealing faint temperature variations that act as a cosmic blueprint. These patterns aren't random, they're the stretched-out imprints of quantum ripples from the universe's first moments. Some researchers believe these ripples hold the key to understanding the inflaton field, the hypothetical energy field that drove inflation. Mastering this field could theoretically let us engineer space itself, triggering controlled expansions to create energy or even warp space-time for propulsion. Imagine spacecraft that don't move through space but stretch space around them, riding waves of artificial inflation like cosmic surfers. Of course, the energy scales involved are almost laughably beyond our reach. Inflationary energy densities dwarf anything our particle colliders can produce by a factor of trillions, yet the same was once said of nuclear fission. Breakthroughs in quantum vacuum research and metamaterials are hinting at ways to mimic inflationary conditions in the lab. Some experiments with supercooled Bose-Einstein condensates already simulate spacetime expansion, offering glimpses into how inflation might be tamed. The real payoff might not be in replicating the Big Bang, but in refining our cosmic toolkit. The same mathematics that describe inflation are now helping astronomers detect gravitational waves and map dark matter. The precision required to study the cosmic microwave background has spun off advances in quantum sensors and cryogenic cooling technologies that now boost everything from medical imaging to quantum computing. What makes cosmic inflation so thrilling isn't just its scale, it's the audacity of the questions it forces us to ask. If the universe could engineer its own birth, what stops us from borrowing those blueprints? The answer might lie in the next generation of telescopes, probing ever deeper into the microwave background's secrets. Every new dataset, every refined model brings us closer to a staggering possibility that the universe didn't just give us a home, it left the instructions for rebuilding it. Quantum foam might sound like something from a physicist's dream, but it could be the very fabric of reality itself. At scales a billion trillion times smaller than an atom, space-time isn't the smooth, unbroken surface we perceive. It's a seething, turbulent sea of virtual particles popping in and out of existence. These fleeting fluctuations, predicted by quantum mechanics, create a frothy, dynamic structure where space and time lose their familiar meaning. For decades, this was pure theory, but recent experiments with ultra-sensitive gravitational wave detectors and quantum-entangled systems are starting to reveal hints of this chaotic underpinning. The implications are staggering. If we could somehow stabilize or manipulate this quantum foam, we might unlock technologies that border on magic. Imagine teleportation devices that don't just move particles but bend space-time itself, creating shortcuts across the universe. Or energy harvesters tapping into the zero-point fluctuations of the vacuum, drawing power from the endless dance of virtual particles. Some theoretical models even suggest that mastering quantum foam could lead to space-time engineering, crafting warp bubbles or artificial gravity fields by controlling the microscopic texture of reality. Of course, the challenges are as immense as the possibilities. Probing the Planck scale requires energies far beyond anything our particle colliders can produce, equivalent to packing the entire mass of a mountain into a single proton. Yet, indirect methods are offering workarounds. Scientists are studying the subtle distortions in light from distant quasars, searching for signs that space-time foam alters their paths over billions of light years. Others are using superconducting quantum interference devices, or SQUID, to detect minute anomalies in magnetic fields that might betray the foam's presence. What makes this pursuit so compelling isn't just the far-off promise of revolutionary tech, it's the immediate impact on our understanding of physics. Quantum foam sits at the heart of the greatest unsolved problem in science, unifying quantum mechanics with general relativity. Every experiment, every theoretical tweak brings us closer to a theory of quantum gravity, whether it's string theory, loop quantum gravity, or something entirely new. The foam isn't just a curiosity, it's a testing ground for the next paradigm in physics. And then there's the philosophical shift. If space-time is fundamentally frothy and uncertain, what does that say about the nature of reality itself? Are the constants of physics truly constant, or do they fluctuate in this quantum sea? Could civilizations advanced enough to manipulate the foam rewrite the very rules of their universe? These questions might seem abstract now, but they're the kind that have a habit of transforming into tomorrow's breakthroughs. The beauty of quantum foam research is that it's as much about the journey as the destination. Every failed detection refines our models. Every new mathematical framework sparks fresh ideas. Whether we ever harness the foam's power or not, the act of probing it is stretching the boundaries of human ingenuity, one Planck-length step at a time. The universe doesn't just host stars, it offers blueprints for civilizations bold enough to re-engineer them. Take Tabby's star, a distant sun whose erratic flickering baffled astronomers. Some speculated its unusual light patterns might stem from a vast swarm of orbiting structures. a Dyson sphere under construction by an advanced civilization harvesting its star's energy. While natural explanations like dust clouds now seem more likely, the audacity of the idea remains electrifying. Imagine engineering on a cosmic scale, vast solar collectors encircling an entire star, capturing its radiant output not in paltry percentages but in full. The energy yield would be mind-bending, enough to power supercomputers simulating entire universes or interstellar arcs voyaging for millennia. Building such megastructures would demand technology that sounds like science fiction, yet we're already laying the groundwork. Self-replicating robots, for instance, could mine asteroids autonomously, churning out solar panels and support structures without human intervention. NASA asteroid redirect mission and private ventures like Planetary Resources prove we're serious about off-world resource extraction. Meanwhile, breakthroughs in 3D printing and nanotechnology hint at future machines that could reproduce themselves using raw materials found in space, turning entire asteroid belts into construction sites. The key lies in exponential growth. A single seed factory could theoretically spawn an army of robotic builders, transforming a star system's rubble into a shimmering energy-harvesting web. But the real genius of Dyson spheres isn't just their scale, it's their elegance. Rather than fighting physics, they embrace it. A swarm of orbiting collectors wouldn't need to defy gravity or invent impossible materials. It would work with orbital mechanics, balancing solar pressure against gravitational pull. Modern solar sail experiments, like Japan's Ikaros probe, demonstrate how spacecraft can maneuver using sunlight alone. Scale that idea up, and you've got the makings of a dynamic Dyson swarm, countless mirrors or panels adjusting their positions in a synchronized dance, each one redirecting energy to where it's needed most. What makes this more than a thought experiment is the urgency behind it. As Earth's energy demands grow, so does our need for sustainable solutions. A Dyson sphere represents the ultimate clean energy project: zero emissions, zero resource depletion, just pure stellar power harnessed with minimal waste. The same principles could be applied in miniature around our own sun, with orbital solar farms beaming energy to Earth via microwaves, a concept Japan's space agency plans to test this decade. Perhaps the most tantalizing question isn't whether we'll build such structures, but whether someone already has. SETI researchers scan the cosmos for infrared signatures that might betray the waste heat of a Dyson sphere in action. While we've found no definitive evidence yet, the search itself pushes our technology forward, refining telescopes and algorithms that now spot distant exoplanets with ease. This isn't just about megastructures, it's about mindset. The universe rewards those who think in cosmic terms, who see stars not as distant lights but as engines waiting to be tuned. Whether Tabby's star's dimming was natural or not, it gifted us something far more valuable than answers: a vision of what's possible when we dare to think like a civilization with its eyes on eternity. Antimatter isn't just science fiction, it's nature's most potent energy source hiding in plain sight. When a single gram of this exotic substance meets normal matter, it releases an explosion equivalent to 43,000 tons of TNT. That's not theoretical, we've measured it. CERN Antimatter Factory painstakingly produces about 1/1000th of a gram per year, trapping these volatile particles in magnetic bottles at near absolute zero. Yet every second, Earth's upper atmosphere is peppered with naturally occurring antimatter from cosmic rays, enough that some researchers propose harvesting it from thunderstorms or orbital collectors. The numbers are staggering. Just 10 milligrams could propel a spacecraft to Mars in under a month, compared to conventional rockets needing 6. The challenge isn't just production, it's containment. Antimatter annihilates instantly upon contact with any normal container wall. so we must suspend it in electromagnetic traps so precise they make Swiss watches look crude. Recent breakthroughs with penning traps, which use rotating electric fields to corral antiprotons, have extended storage times from minutes to months. Even more promising are experiments with neutral anti-hydrogen atoms, chilled with lasers to near motionless states where they can be studied and eventually stored more safely. Imagine future spacecraft with antimatter fuel tanks resembling intricate magnetic sculptures, their invisible fields cradling volatile cargo like cosmic eggshells. What makes antimatter truly revolutionary isn't just its energy density, it's the cleanliness. Unlike nuclear reactions that leave radioactive waste, matter-antimatter annihilation converts mass directly into pure energy with 100% efficiency according to Einstein's famous equation. No greenhouse gases, no toxic byproducts, just gamma rays that could be harnessed for propulsion through magnetic nozzles. NASA concept vehicles like the AIM-STAR probe envision using microfrozen antimatter pellets to ignite inertial confinement fusion, creating controlled bursts that push spacecraft to relativistic speeds. The cosmic irony: the universe seems to favor matter overwhelmingly, with antimatter appearing only fleetingly in particle collisions or extreme astrophysical events. Some theories suggest primordial black holes might be natural antimatter factories, while others propose mining Jupiter's radiation belts where cosmic rays generate temporary antimatter clouds. The real game changer might come from unexpected quarters. Quantum physics hints that vacuum fluctuations could be coaxed into producing particle-antiparticle pairs, potentially turning empty space itself into the ultimate fuel depot. Beyond propulsion, antimatter could revolutionize medicine. PET scanners already use positrons' antimatter electrons to image cancers with millimeter precision. Next-generation antimatter therapies might target tumors directly, their precise annihilation releasing energy exactly where needed to kill malignant cells while sparing healthy tissue. Even materials science stands to benefit. Studying how antimatter interacts with matter at quantum levels could reveal new superconductors or energy storage mediums. The obstacles remain daunting. Scaling production from nanograms to milligrams would require particle accelerators encircling entire cities, and containment failures could prove catastrophic. Yet history shows that what begins as laboratory curiosity often becomes commonplace technology. The same skepticism once met nuclear power and spaceflight now fuels our brightest ambitions. Antimatter doesn't represent just another fuel option, it's the ultimate benchmark, the energy source against which all others are measured. Its pursuit isn't merely about reaching Mars faster, it's about proving that humanity can harness the universe's most extreme physics, turning annihilation into creation. Plasma isn't just the stuff of stars, it's the fourth state of matter that could power our future here on Earth. Picture the sun's roiling surface, where temperatures soar to millions of degrees and atoms are ripped apart into a swirling soup of charged particles. This superheated plasma, threaded with intricate magnetic fields, doesn't just light our solar system, it holds the key to unlocking unlimited clean energy through nuclear fusion. Laboratories worldwide are racing to recreate these stellar conditions in donut-shaped reactors called tokamaks, where powerful magnets contain plasma hotter than the sun's core. The goal: to harness the same process that fuels stars, but in a controlled, earthbound environment. The challenges are as immense as the potential rewards. Containing plasma is like trying to grip a lightning bolt. It twists, writhes, and escapes at the slightest instability. Yet recent breakthroughs are turning science fiction into reality. The International Thermonuclear Experimental Reactor, or ITER, in southern France uses superconducting magnets cooled to near absolute zero to cage plasma at temperatures exceeding 150 million degrees. Meanwhile, private ventures like Commonwealth Fusion Systems are pioneering smaller, more efficient reactors using revolutionary high-temperature superconductors. These aren't just incremental improvements, they represent leaps toward the long-dreamed of fusion power plant that could provide carbon-free energy with seawater as fuel and helium as the only byproduct. But the applications don't stop at energy production. The same physics governing stellar plasma could revolutionize propulsion for interstellar travel. Imagine spacecraft engines that don't burn chemical fuel but instead create miniature stars in magnetic bottles, their controlled fusion reactions generating exhaust velocities thousands of times faster than conventional rockets. Projects like Princeton's Field Reversed Configuration Experiment are already testing compact plasma thrusters that could slash travel time to Mars from months to weeks. Even more ambitious are designs for magneto-inertial fusion drives, which would use pulsed magnetic fields to ignite tiny fusion explosions, essentially creating controlled supernova for propulsion. Perhaps the most futuristic application lies in force field technology. Plasma, when magnetically contained and ionized, can deflect radiation and even physical projectiles. The U.S. military has explored plasma-based shields to protect spacecraft from cosmic rays, while aerospace companies are developing plasma windows that could maintain atmospheric pressure in space stations without physical barriers. On a smaller scale, researchers have created plasma scalpel beams that can cut with nanometer precision for medical surgeries, their paths guided by magnetic fields in ways that steel blades could never match. What makes plasma physics so extraordinary is its universality. From the auroras dancing in Earth's polar skies to the jets streaming from distant quasars, plasma dominates the observable universe. By learning its rules, we're not just copying nature, we're joining a cosmic conversation that's been ongoing since the first stars ignited. Every tokamak experiment, every fusion breakthrough, every new plasma application brings us closer to speaking the language of the stars themselves. The day we truly master this fourth state of matter won't just transform our technology, it'll redefine our place in the universe. Gravitational waves aren't just cosmic echoes, they could be the universe's ultimate messaging system. When LIGO first detected these ripples in spacetime from colliding black holes over 1 billion light-years away, it wasn't just proof of Einstein's century-old prediction. It revealed a fundamental truth: the fabric of reality itself can carry information across unimaginable distances. Unlike light, which gets absorbed or scattered by cosmic dust, gravitational waves pass through everything: stars, planets, entire galaxies without distortion. That makes them the perfect carrier for communication on scales where radio signals would take millennia to arrive and arrive hopelessly degraded. Imagine an advanced civilization encoding data in the spiral dance of neutron stars before their cataclysmic merger. The precise timing of their final orbits could carry vast amounts of information in the gravitational waves they emit, a cosmic Morse code written in spacetime itself. Future observatories like LISA, a space-based gravitational wave detector set to launch in the 2030s, could potentially decode such signals if they exist. These wouldn't be simple hello messages either. The complexity of merging compact objects offers bandwidth that could theoretically transmit entire libraries in a single collision. The engineering challenges are staggering but not insurmountable. While we can't yet create gravitational waves strong enough for practical use, nature provides abundant natural transmitters. Some theorists propose using carefully timed asteroid impacts on neutron stars to generate detectable waves, a primitive but conceivable starting point. More advanced concepts involve artificial black hole binaries kept in stable orbits, their controlled collisions broadcasting precisely modulated signals across intergalactic distances. Even without active transmission, civilizations might use naturally occurring wave events as synchronization markers. Cosmic clock ticks to align calendars across star systems. What makes this more than speculation is how gravitational wave astronomy is already evolving. Current detectors like LIGO and Virgo can pinpoint wave sources to broad regions of sky, but next-generation arrays could localize them to individual star systems. This precision navigation capability might one day allow spacecraft to triangulate their position using gravitational wave landmarks, a galactic GPS based on the steady rhythm of colliding black holes rather than satellites. The same technology could create an early warning system for catastrophic astrophysical events, giving colonies years to prepare for incoming gamma-ray bursts or nearby supernova. The most profound implication lies in the waves' timeless nature. Because they travel at light speed without degradation, a sufficiently advanced receiver could detect messages sent billions of years ago, or by civilizations that died out before Earth formed. This transforms the search for extraterrestrial intelligence from a spatial hunt across the galaxy to a temporal excavation of cosmic history. Gravitational wave observatories might one day serve as archaeological tools, sifting through spacetime's background hum for the faint but deliberate patterns of intelligence. Unlike radio SETI, which assumes aliens think in electromagnetic terms, gravitational wave communication requires no such anthropomorphic assumptions. Any sufficiently advanced civilization would inevitably discover these ripples in spacetime and recognize their potential as the universe's most reliable information highway. The quietest whispers of colliding black holes could be carrying the richest conversations we've ever imagined if only we learn to listen properly. This isn't just about building better detectors. It's about recognizing that the universe has been providing the perfect communication channel all along. We just needed the tools and the imagination to recognize it. Every new gravitational wave event we observe could be carrying more than astrophysical data. It might be the first page in a cosmic encyclopedia we're only beginning to read. Exotic matter defies everything we know about the building blocks of reality, where atoms give way to forms so bizarre they seem plucked from a physicist's wildest dreams. Deep inside neutron stars, where gravity crushes matter into oblivion, protons and electrons may dissolve into a sea of free-floating quarks, the fundamental particles that normally bind together in tidy triplets. This strange quark matter could be the ultimate cosmic alchemy, a state where up, down, and strange quarks mingle freely, creating substances hundreds of times denser than anything on Earth. If we could synthesize even a speck of this material, it might revolutionize technology overnight. Picture superconductors that operate at room temperature, effortlessly carrying electricity without resistance, enabling lossless power grids and levitating trains that glide on quantum rails. But quark matter isn't the only exotic state rewriting the rules. Bose-Einstein condensates, formed when atoms are chilled to within a whisper of absolute zero, behave less like particles and more like waves merging into a single quantum entity. In labs from MIT to the International Space Station, scientists are manipulating these ghostly condensates to mimic cosmic phenomena, creating artificial black holes to study how they evaporate, or simulating the birth of the universe itself. The real magic lies in their potential to engineer materials with negative mass, where pushing an object makes it move toward you instead of away. Imagine spacecraft propulsion that doesn't rely on fuel, but on manipulating inertia itself, or construction materials that reinforce themselves under stress instead of cracking. The irony is profound. To reach the future, we might need to dismantle the periodic table altogether. For centuries, chemistry has focused on combinations of protons, neutrons, and electrons. But what if the next industrial revolution springs from phases of matter that don't even exist naturally on Earth? Projects like CERN quark-gluon plasma experiments and quantum labs studying ultra-cold condensates are already blurring the line between materials science and astrophysics. Each discovery peels back another layer of possibility, suggesting that the true periodic table isn't the one hanging in classrooms. It's a hidden catalog of extreme states waiting to be unlocked, from quark soups to time crystals. The implications stretch far beyond labs. Strange quark matter, if stable at terrestrial pressures, could become the ultimate energy storage medium, a sugar cube-sized fragment holding the equivalent of a nuclear power plant's yearly output. Negative mass condensates might lead to inertial dampeners, canceling the G-forces that limit human space travel. Even medicine could transform, with quantum condensates enabling ultra-precise sensors to detect diseases at the molecular level. What makes this frontier so electrifying isn't just the technologies, it's the mindset shift. We're no longer limited to rearranging the universe's given pieces. Now, we're learning to invent entirely new rules, crafting matter as nature never intended. The neutron stars and quantum labs are whispering the same message. The elements we know are just the first page of a much stranger textbook. The sun isn't just our nearest star. It's a raging powerhouse whose violent outbursts could rewrite the rules of energy here on Earth. Solar storms, those colossal eruptions of charged particles and magnetic fury, typically make headlines for their destructive potential, knocking out satellites, disrupting power grids, and scrambling communications. But hidden within their chaos lies an astonishing opportunity. These storms carry enough energy to power human civilization for centuries if we could just learn to harness them. Picture a coronal mass ejection, a billion-ton cloud of plasma hurled from the sun's surface at millions of miles per hour. When this tsunami of charged particles slams into Earth's magnetic field, it doesn't just create auroras, it induces massive electrical currents in our planet's crust. In 1989, one such storm blacked out Quebec's power grid in seconds, yet that same event pumped enough energy into Earth's magnetic field to power New York City for months. The trick lies in capturing it. Researchers are now exploring massive ground-based induction coils that could convert these geomagnetic surges into usable electricity, effectively turning our entire planet into a cosmic battery charger. But the real frontier lies beyond our atmosphere. Solar storms accelerate particles to near light speed, creating natural particle beams far more powerful than any human-made accelerator. NASA Parker Solar Probe has revealed how spacecraft could surf these charged waves using magnetic sails, riding solar wind like ships catching a cosmic breeze. Unlike traditional rockets that carry finite fuel, these vessels would tap into an endless stellar resource, accelerating continuously toward the outer solar system. Private ventures are already testing scaled-down versions, with prototypes using plasma brakes to maneuver using nothing but solar wind pressure, the most radical idea. Deliberately triggering controlled solar storms, by focusing high-energy lasers or particle beams on specific regions of the sun's corona, we might one day stimulate localized eruptions on demand, creating clean, directed energy bursts for spacecraft propulsion or remote power transmission. It sounds like science fiction, but labs are already experimenting with miniature versions using plasma chambers that mimic solar dynamics. Of course, the challenges are as immense as the potential. Predicting solar storms remains frustratingly imprecise, and harvesting their energy requires infrastructure capable of withstanding sudden, massive surges. Yet every advance in space weather forecasting, like the National Oceanic and Atmospheric Administration's Discover satellite, brings us closer to taming this cosmic force. The same AI models developed to predict solar flares are now optimizing wind farms and power grids here on Earth, proving that space weather research pays dividends long before we build the first solar storm power plant. This isn't about conquering nature's fury, it's about learning its rhythms. The sun has been bathing planets in energy for billions of years. We're just beginning to understand how to work with its cadence rather than suffer its tantrums. From storm-proof satellites that recharge from geomagnetic turbulence to interplanetary freighters sailing on particle winds, the future of energy might not lie in digging deeper into Earth, but in reaching upward to embrace the sun's fiery generosity. Cosmic strings aren't just theoretical oddities, they might be the universe's original power grid, woven into the fabric of reality itself. Picture these hypothetical threads, thinner than a proton but stretching across the entire cosmos, left over from the universe's violent birth. According to some models of the Big Bang, as space-time cooled and expanded, cracks might have formed in its structure, like fissures in ice as it freezes. These cracks would be unimaginably dense, packing the mass of entire stars into filaments just a kilometer long. A single inch of cosmic string could outweigh Mount Everest, warping space around it so intensely that it would act as a gravitational lens, bending light from distant galaxies into perfect twin images. The potential applications sound like pure science fiction, but the physics behind them is anything but. A cosmic string's incredible tension could be used to stabilize wormholes, creating shortcuts through spacetime that wouldn't collapse instantly under their own gravity. Imagine spacecraft threading these cosmic tightropes to cross galactic distances in the blink of an eye. Even wilder is the time travel angle. Two cosmic strings moving past each other at near light speed would warp spacetime so severely that closed time-like curves, theoretical pathways to the past, could form. While we've never detected a cosmic string directly, their mathematical elegance is undeniable. They emerge naturally from attempts to reconcile general relativity with quantum mechanics, the holy grail of modern physics. What makes cosmic strings so tantalizing isn't just their speculative uses, it's how studying them pushes technology forward. The same equations describing these spacetime flaws are now helping engineers design ultra-sensitive gravitational wave detectors. Quantum computers are borrowing string-inspired models to create more stable qubits. Even materials science is benefiting. Researchers are mimicking cosmic string geometry to develop superconductors that work at higher temperatures, threading atoms into defect lines that carry current without resistance. The hunt for cosmic strings has already revolutionized astronomy. Telescopes scour the sky for telltale double images of distant galaxies or sudden flashes from strings snapping like cosmic guitar strings. While we wait for definitive proof, the search itself is rewriting our understanding of the early universe. Whether we find them or not, cosmic strings represent something profound. The universe might be threaded with relics of its birth, waiting to be repurposed by civilizations bold enough to grasp them. The same forces that shaped reality could one day become its most powerful tools. Terraforming isn't just science fiction, it's the ultimate test of planetary engineering, where the brutal landscapes of Mars and Venus become proving grounds for technologies that might one day save Earth. Picture Mars with its wispy atmosphere, barely 1% as thick as Earth's, where sunlight barely warms the frigid surface. Then swing past Venus, shrouded in clouds of sulfuric acid with surface temperatures hot enough to melt lead. These aren't just inhospitable worlds, they're blank canvases for humanity's most ambitious project, reshaping entire planets to suit our needs. The strategies for each couldn't be more different. On Mars, the challenge is building up, thickening the atmosphere to trap heat and shield against radiation. Scientists are testing extremophile algae and cyanobacteria in simulated Martian conditions, organisms that could theoretically survive the harsh environment while converting carbon dioxide into oxygen. Some designs propose crashing icy asteroids into the planet to release water vapor and greenhouse gases, jump-starting a warming cycle. More radical ideas include orbital mirrors the size of Texas, focusing sunlight onto polar ice caps to release trapped carbon dioxide in carefully controlled bursts. Venus presents the opposite problem: how to cool a runaway greenhouse effect. Here, the solutions read like something from a cosmic HVAC manual: floating cities in the temperate upper atmosphere, where air pressure and temperature are nearly Earth-like. Below, massive solar shades could block sunlight, while genetically engineered bacteria might convert atmospheric sulfur into stable minerals. Some researchers even speculate about bombarding Venus with magnesium and calcium to chemically bind with atmospheric carbon, creating a solid crust from the planet's toxic sky. What makes these projects more than thought experiments is how they're already influencing Earth's climate tech. The same algae being tested for Mars could help sequester carbon in our oceans, while Venus-inspired solar reflectors might cool overheating cities. Even asteroid redirection research, crucial for delivering water to Mars, doubles as planetary defense practice against real impact threats. The most profound lesson lies in perspective. Trying to fix planets forces us to see Earth not as an isolated system, but as one fragile balance among many. Every calculation about atmospheric pressure on Mars refines climate models here. Every Venusian cooling experiment sharpens our understanding of greenhouse gases. We're not just rehearsing to remake worlds, we're compiling a universal survival manual, one where the skills to nurture a dead planet back to life might just preserve our own. The universe generates more data in a single second than humanity could process in a lifetime, but artificial intelligence is changing the game. Telescopes like the Vera Rubin Observatory now scan the sky nightly, capturing petabytes of cosmic information that would take human astronomers centuries to analyze. Enter machine learning algorithms trained to spot the celestial needles in this digital haystack. These AIs don't just catalog known phenomena, they hunt for anomalies, flagging strange flickers in distant galaxies or gravitational lensing patterns that defy conventional models. In 2023, one such algorithm discovered a bizarre object orbiting a neutron star, a potential quark nova that theorists had predicted but never observed. The AI spotted it in days, while traditional methods might have missed it entirely. What makes this revolutionary isn't just speed, it's the way these systems think differently. Human astronomers are constrained by cognitive biases, instinctively searching for patterns that match existing theories. Machine learning operates without such blinders, detecting correlations invisible to our neural wiring. Take fast radio bursts, those mysterious cosmic signals that puzzled scientists for years. AI analysis recently revealed subtle subclassifications in their waveforms, hinting at multiple origins that could rewrite our understanding of stellar cataclysms. Other algorithms are mapping dark matter distributions with unprecedented precision by identifying gravitational distortions in galaxy clusters that human eyes gloss over as noise. The next frontier, AI as cosmic architect. Neural networks are already simulating galaxy formation with startling accuracy, compressing billions of years of evolution into hours of computation. Some teams are feeding these models exotic physics, modified gravity theories, higher dimensional spacetime, even warp metric equations, to see what stable configurations emerge. The results are mind-bending. Hypothetical warp bubble geometries that don't violate known physics, or wormhole solutions that previous mathematicians dismissed as untenable. One Google DeepMind project accidentally rediscovered a forgotten Einstein equation while training an AI to optimize energy distributions in curved spacetime. These aren't just academic exercises, they are blueprints for future technologies. Consider the challenge of designing a functional Alcubierre warp drive. The math involves manipulating spacetime itself, requiring solutions to hundreds of interdependent field equations. Human teams have struggled with this for decades, but AI systems like MIT's Space-Time Engine can iterate through millions of configurations in days, identifying stable warp field geometries that traditional approaches overlook. Though we lack the exotic matter to build such drives today, these simulations provide something equally valuable: proof that the universe's rulebook might allow shortcuts we're only beginning to comprehend. The most tantalizing possibility lies in artificial cosmologists, AIs tasked with simulating entire universes with alternate physical constants. By running countless variations, these systems could identify which laws of physics naturally lead to stable, complexity-friendly environments. The implications are staggering. We might uncover hidden relationships between gravity and quantum mechanics, or discover that our universe's constants aren't arbitrary but inevitable outcomes of deeper meta-laws. Some theorists believe this approach could crack the hierarchy problem: why gravity is so weak compared to other forces, a puzzle that stumped physicists for half a century. Yet the true power of cosmic AI isn't just in solving known puzzles, it's in revealing questions we never thought to ask. When an algorithm trained on quasar spectra detected an unexpected periodicity in their redshifts, it led astronomers to propose a radical idea. The universe might have higher dimensional topology, with light echoing through folded spacetime like sound in a cathedral. Whether this hypothesis holds or not, it demonstrates how machine intelligence can serve as a compass pointing toward uncharted theoretical territories. The next paradigm-shifting discovery in astrophysics might not come from a lone genius scribbling equations, but from an AI system connecting dots across petabytes of data that no human could hold in their mind at once. This partnership between silicon and stars isn't about replacing human curiosity, it's about amplifying it. The greatest telescopes extend our vision, machine learning extends our cognition. Together, they're rewriting what's possible in our quest to understand, and perhaps one day navigate, the cosmos. The universe has been broadcasting its secrets for billions of years. With AI, we're finally learning how to listen at its wavelength. From dark matter to quantum foam, the universe doesn't just whisper its secrets, it shouts them in bursts of gamma rays, in the eerie silence between pulsar pulses, in the ghostly trails of neutrinos slipping through our planet like moonlight through glass. These aren't just riddles for astronomers to ponder, they're blueprints waiting to be traced by engineers, inventors, and dreamers. Consider how the hunt for dark matter detectors birthed quantum sensors so precise they can map underground mineral deposits from orbit, or how studying neutron stars led to atomic clocks accurate enough to measure continental drift in real time. The cosmos isn't a passive backdrop, it's an active collaborator, offering solutions we're only beginning to recognize. Look at history's greatest leaps. Einstein's relativity wasn't just abstract math, it became the GPS in your phone. Quantum mechanics wasn't confined to chalkboards, it birthed the silicon chip. Today's cosmic mysteries hold that same explosive potential. The same quantum foam that makes empty space seethe with virtual particles could one day power computers that solve climate change in seconds. The gravitational waves rippling from colliding black holes might inspire propulsion systems that bend spacetime itself. Even the most esoteric theories like white holes spewing matter or cosmic strings threading the universe aren't mere thought experiments. They're stress tests for our imagination, pushing us to invent materials, energies, and technologies that sound impossible until they're inevitable. What makes this moment extraordinary is how democratized the tools have become. You don't need a billion-dollar lab to contribute open-source AI models analyze telescope data. Citizen scientists spot anomalies in particle collision records, and startups prototype fusion reactors in garages. The barrier between out there and right here is dissolving. When a high school student using public satellite data identifies a potential Dyson sphere candidate, or a YouTuber's homemade plasma chamber replicates conditions near a neutron star, it proves the cosmos isn't just for elites in ivory towers. The next civilization-shifting breakthrough could come from a basement, a classroom, or a coffee shop where someone dares to reinterpret the universe's clues. This isn't about passively waiting for aliens to share their tech or hoping for some deus ex machina to save us. It's about rolling up our sleeves and reverse engineering nature's greatest hits. Every time a physicist tweaks an equation to stabilize a wormhole or a biologist engineers extremophile DNA for Mars, they're doing more than science. They're rewriting humanity's job description. We're no longer just inhabitants of the universe. We're becoming its mechanics, its architects, its students. The night sky isn't a ceiling, it's a workbench. And the tools, they've been lying in plain sight all along, forged in supernova and coded into quantum fluctuations, waiting for us to look up and ask, what can we build with this? So while the stars may seem distant, their lessons are closer than you think. That smartphone in your palm owes its existence to our ancestors studying the heavens. The future in your imagination. It's already taking shape in labs where dark matter meets quantum computing, where asteroid mining intersects with AI, where the line between science fiction and science fact blurs a little more each day. The universe isn't just revealing its secrets, it's inviting us to play. All we have to do is reach out and